Hi, this is the third lecture on path connectedness, possibly the last one, and this is part of the topology and connectedness series. And the main result of today's session is an example of a connected space which is not path connected. In literature, there are two standard examples. One is the so-called cone space, the other one is the topology sine curve. And you may remember we had already come across cone space in one of the examples. Do you remember where we did? When we wanted to show if A is connected, A is a subset of B and B is a subset of A closure, then A B is also connected. In particular, A closure is connected. As an example of a B which is strictly between A and B closure, we looked at the cone space. Okay, and also in my practice, I find that the students understands and appreciates the cone space much better than topology sine curve. Okay, but in case you want me to lecture on topology sine curve also, please send me an email to the email given in this notes, okay, in this video, and I will produce one. Okay, let us get started. Let me start the timer. Right. So if any kind of contact you want to do, you just send it to this email ID. Okay, and please inform your friends and juniors who are interested in learning mathematics, and those who do not look only for grades, suggest them my channel. And this is path connectedness 3 on 7th December. The email ID is again given here. References as in connectedness 1. Okay, so before we go further, let me finish one important application of a result which we did last time. Last time we proved if X is a connected space, if U is an open subset of Rn and U is connected, that implies U is path connected. Right? This was the result. I want an application of this here. Since we are already exceeding my time, so I stopped it, but let me finish this first. You may remember we proved GL and R, the set of invertible matrices, as a subset of M and R. We showed this is an open set and this is Rn squared, and the topology was norm of A could be any one of the topologies, maximum mod Aij, etc. Okay, so with respect to this visit, and we also showed this is open but not connected. Why it was not connected? If I look at the determinant function from GL and R to R, the image is R star. This is not connected, right? Therefore this is not. But you can ask what happens if I look at GLN plus R, that is the set of matrices A in M and R, so that determinant of A is positive, right? Now notice that by whatever we did, determinant function from this space Rn squared to R given by X going to determinant X, this we know is a continuous function, right? And we want to know what this is, determinant of X. Okay, let us look at 0 to infinity, determinant inverse. Okay, this is M and O, this is GLN plus R, right? So if I know this is connected, then it will follow it is path connected. right? Yeah, because what is our assumption? If it is open set which is also connected, it is path connected. Okay, so one can wonder whether it can prove connectedness. Okay, so is this true? So there are various means of seeing this. Okay, but I don't want to spend more time on that, but think about. Okay, the easier one maybe, let us look at, okay, let's not worry about, just think about it. Okay, yeah, now let's come back to the Combs space. So how did you do? Let me look at, this is my R2, and at each 1 by n, okay, this is 1, I define A1, this is a line y equal to 1, and this is half, I have this line again, that doesn't look nice, right? Yeah, and this is 1/3, and this is 1n, and this is 0, and this is the point P, and P is the point 0, 1. So let us look at what is our space. Combs space X is consisting of singleton P union this L, this is the line L, and union ANs. So what is L? L is a subset x comma 0, 0 less than or equal to x less than or equal to 1. That is this line. This is my L. Okay, and what are ANs? ANs are set of all points, okay, 1 by n comma y, where 0 less than or equal to y less than or equal to 1. Okay, n natural number. I am starting from n equal to 1 onwards. Okay, right. So I hope all of these things are done. What you have shown is this, of course, is the subspace topology as a subset of R2. This is a subspace topology on X. And first notice that L union AN, let me write it AN, 1 n union L, this is connected. Why this is connected? This is one of the earlier results. Do you remember? If A's are connected, B is a connected set, such that A intersection B is non-empty for all I, then union AI union B is connected. Okay, for example, if you think of a continuous function from here to plus or minus 1, okay, then it has to be constant on any AN, and it has to be constant on this L, but they have a point in common, therefore it is constant. So etc., right? Always, whenever you see such things, don't assume that you have seen it. Okay, then you most often you will not feel confident to go through the proof in your mind. Make it a practice to go through such things. Even if you get halfway, that's fine. Slowly you will build up a lot more confidence, and you will be able to get the proof 100% correct also later. With this requires practice. Please do that. You see that I just went through the proof again. Okay, this is how I do usually. Okay, anyway, so we know union AN union L is connected, right? Now let's look at the set of X. Okay, it consists of P union this B, call this is B if you want. Okay, and now P is a class an adherent point of B. Why it's an adherent point? Let us look at all these fellows who are at the top, 1 by n comma 1, and where do they converge in the subspace topology? They converge to 0 comma 1, right? Remember, this is a metric space topology, right? Therefore these are the points in B, and they converge to a point, therefore this limit must be an adherent point. All these things. Now do you see why it is important to understand and appreciate much better? If you simply think of a theorem which you have to learn by heart for exam, you will never feel confident. Everything will look new or very mysterious. Anyway, so Therefore what you have shown is X is connected. This we had already seen. I repeated the proof for completeness sake. Okay, please pause, review, and then proceed. Let me make sure I started the yeah, right. See, at some time I become I forgot to start the recording anyway, right? Now I just want to say X is not path connected. Okay, now let's look at the picture. Where do you think, can you think of 2 points, right, which for which there is no path which connects them? I want you to think of 2 points, call it something like A and B, and this is not the subset A, okay, some A and B, and said that A is not path connected to B, or A and B are not path connected. Can you think of some point? One point should be obvious to all of you. What is that point? P, correct? Because that looks, this is the one which is somewhat mysterious. Okay, it looks as though it's difficult to imagine why this space should not be connected, but we are claiming it's connected. Okay, this is the point which causes some problem for the beginners. Okay, but we have proved that it is connected space. So, but if I start with the path from that point P0, 1, 0, 1, and it has to go like somewhere to reach some point here. Again, I can think of which point I want. Okay, I can think of the points, for example, 1, 0, or okay, this is 1, 0 or 1, 1, right? So what we want to claim, okay, we claim, okay, there exists no path connecting P to Q, where Q is 1, 1. In fact, for any point I could have taken, okay, don't worry, I could have taken any point of X other than P. Okay, it's not going to be path connected. But if once you go through this proof, you will understand. Okay, there is no speciality about my Q. Q could be any point of X other than P. Anyway, so before going to the proof, let us go very slowly so that you should feel confident. Okay, let us look at the picture. Okay, now I am not going to be very precise. My pictures may not look very nice and all that, but don't worry. Right? Okay, the point has to be somewhere here. Okay. Now let us look at a small, let me call it small p. Okay, small p and small q, so that it will be easier for me to write to R. Suppose R is positive and said that B of, okay, is said that it does not intersect x-axis. Okay, look at the picture. So there will be a lot more things. A lot more lines here, right? You understand? So this, therefore BP of R intersected X is an open neighborhood of P, right? Now do you see what are the path connected components? Components of BP of R intersection with X. Let me just magnify the picture again. My picture may not be very good. I hope all of you will agree whatever I'm trying to draw. Okay, this is my P, right? This is at 1, 0, therefore things will be like this. These are the lines which will be there. Notice that as you go, these should be very, very close to each other, but it will be very difficult for me to draw. Okay, so BP of R, okay, maybe I should have used a different color so that it will be easier. These are the points which will be there. Okay, this all this coffee color one, okay, they are going to be the connected components. Yes, do you follow that? Why each one of them is a connected component? Because these are all line segments. This is a singleton line component. Okay, so that's it. Right, next thing what I want is, let us assume there is a path gamma, okay, is a path 0 1 to x, so that let's assume gamma 0 is p, which is 0 comma 1, and gamma 1 is q, which is 1 comma 1. Right? Okay, now what I'm going to do, I'm going to look at the x component of gamma. So this I can write as gamma 1t as gamma 2t. This is the x coordinate of this point, this is the y coordinate, so I will write it as x comma t, x of t, y of t. Okay, x of t is nothing other than gamma 1 of t. X of t is nothing other than the x component of gamma t. Do you understand that? Okay, now let's look at the map t going to x of t. This is continuous. Do you agree with that? Why this is continuous? Because t going to gamma t is continuous, followed by the projection onto the first factor. That's a continuous thing. From R2 to R, the projection map is continuous. It's a first degree polynomial, we know that. So this is a continuous map. Do you follow that? Okay, therefore, okay, I want to say something. Okay, before I say something, for the third thing, now since B P R, remember it does not intersect the x-axis. Okay, now since BP of R intersection capital X is an open relay, okay, set in the subspace topology, right, and gamma is continuous. Gamma is continuous from 0 1 to 1 to x, continuous, right? Therefore, given this, there is, and remember, and gamma of 0 is p, therefore there exists a delta, okay, so that gamma of 0 delta should be contained in BP of R, of course intersection x, because gamma takes values only in x. Do you follow that? This is by continuity. It is continuous at 0. I have given an open set containing gamma of 0, therefore there exists an open set containing 0 which is mapped into this set. Okay, I hope all of you understand continuity well. Okay, this is what happens. Do all of you agree with that? Okay, now remember, since gamma is continuous, and what do I know about this interval 0 delta? This is a connected subset of R, because any interval is a connected subset of R, and these are the only ones which are connected subsets. Okay, therefore gamma, okay, therefore x of the, remember my x is gamma 1, okay, x of 0 delta, this is a connected subset of R. Do you agree with that? Yeah, that is, you are looking at gamma of 0 delta and take the projection onto the first factor. Okay, this is a this is a subset of R and it must be connected. Okay, pause, review, proceed. Right, now let's look at where does gamma t lives here. If it say it, you say it lies here, intersection S, then it may be here or it may be one of the ends. You understand this? That's a picture which I took. Okay, this is my thing. Yeah, because gamma t, this is t, not 1. Okay, the x consists of only these things. BP of intersection x is only these part of the line segments and this point. Do you follow that? And therefore what are the x coordinates? If okay, xy, the point belong to BP of R intersection x. Again, this x is not the function x. Okay, if you want, keep it as pi 1 composite gamma. Okay, this one belong to that. Then x, what are the possible values? X has to take values in 0 union 1 by n, where n is a natural number. In fact, we even know what should be that n. Okay, this, are you following? Yes, right. Therefore pi 1 of gamma t for t in 0 delta lies in this set 0 union 1 by n. This n is actually greater than or equal to some capital N. That's because you look at this picture, I have this, okay, this is my p, then these are the one. Okay, so this point will have coordinate 1 by n comma 1, and therefore the distance is 1 by n. Therefore 1 by n should be less than r. That means r should be greater than, sorry, n should be greater than 1 by r. Okay, that is my capital N. Don't worry about such things, but anyway, it's okay. You understand that? But I know this is a connected set, but pi 1 composite gamma of 0 delta is connected, but then it's contained in this set 1 by n, n in n. Okay, now what are the connected components of this? Of this set are singletons, right? And remember, since the gamma of 0 is 0 comma 1, pi 1 of gamma of 0 is 0, 0 belong to this. Okay, 0 belong to this. Therefore, okay, therefore pi 1 of gamma of 0 delta must be a connected set contained in 0 1 union 1 by n, n in n, so that 0 belong to that set. Okay, make sure you understand all these things. Therefore the only connected components of this set, sorry, connected components of this set are singletons, and the point 0 must be in this. Therefore the only thing is, therefore what do I conclude? Pi 1 of gamma of 0 delta, okay, this is singleton 0. Do all of you agree with that? Therefore what does it mean? Therefore for every t in 0 delta, okay, pi 1 of combo t is 0, right? So if I write this as x of t, y of t, then this is point 0 and y of t. And remember, y of t, this must be a point of my space x. This also belongs to BP of R. That doesn't matter. Therefore this y of t should be some 1 over n. That's not important. Okay, are you following? So this is the crucial thing. See, this for every t here, this is 0. But remember, pi 1 composite gamma is continuous, right? And delta belong to 0 1. Therefore it's continuous at delta. Therefore limit t goes to delta of pi 1 composite gamma of t must be equal to pi 1 composite gamma at delta. But this limit is 0 because each one of them is 0. Therefore what we conclude is pi 1 composite gamma at delta is 0. So this is the picture I have, 0 up to delta. Okay, this is 0. Is that okay? Let's not worry about what happens to the y coordinate. This is enough. Okay, so if I write gamma of t as x of t, y of t, if 0 is less than or equal to delta, then this is 0 yt, always of this form. Agreed? Okay, see, pause, review, proceed. Now let's look at, now let us repeat the same thing. Now remember, what should be gamma of delta then? Yeah, as I said, this is 0 comma y of delta. Okay, right. Now this belong to your space X. That's granted, right? Now I can repeat the same process since gamma is continuous at delta in 0 1. Okay, there exists some other delta 1. Let us again have a picture so that life will be easier. Delta plus delta 1, sorry, delta minus delta 1, delta plus delta 1, or simply say delta 1 is greater than this, right? Such that what happens? Gamma maps 0 delta to delta plus open inside BP of R intersection X. Yeah, okay. Now therefore again arguing as above, we see that gamma of delta plus delta 1 must be 0. But if you are not convinced with this kind of argument, I will go back to my usual LEB argument. So let us look at the set T in the interval 0 1 so that phi 1 composite gamma of T is 0. Then we have shown that the entire set 0 to delta is contained in this. Okay, so right, let delta 1 be the LEB of this set. Right, therefore what do I know is gamma of delta 1, phi 1 of gamma of delta 1 is also 0. So I claim delta 1 must be equal to 1. Claim. Suppose not. So this is my 0, this is my delta 1, this is my 1, right? Then use the same argument. Okay, since gamma is continuous at delta 1 etc., then I can find a small neighborhood around this which is contained in 0 to 1, on which for every t here my pi 1 composite gamma of t is again 0. Therefore if this is called delta 2, then again by continuity pi 1 composite gamma of delta 2 is 0, but delta is strictly greater than delta 1, but that is supposed to be LEB of that set, a contradiction. Are you following? Okay, I hope by now you all of you are convinced there is no shortcut. You have to learn the least upper bound, GLB, basic real analysis well. Simply talking about continuity, open sets, compact set, connectedness, that will not take you far. Okay, have you understood the proof? So what I have 0, I have delta 1, this is the LEB of which set of all t in 0 1, so that pi 1 composite gamma of t is 0. Therefore we know pi 1 composite gamma of delta 1 is 0. Now in place of 0, use the continuity of gamma at delta 1. Therefore there exists an open set which is going to be contained in the corresponding thing. Okay, wherever it is b of gamma delta 1 some other r, so that does not intersect with x-axis, intersection with x. Again, the connected components will only look like these points. Okay, the points will look like this. Suppose even assuming it is some other point, if I take, there will be only these kinds of stuff. Okay, the argument is the same. Therefore you will see that, okay, there is a delta 2 which is strictly greater than 1. This is contained in 1. Okay, right. So we will see that phi 1 composite gamma of t is 0 for 0 less than or equal to t less than delta 2. Therefore it will follow phi composite gamma of delta 2 is 0, but delta 2 is strictly greater than delta 1, but delta 1 is the LUB. Okay, therefore this contradiction shows delta 2 must be equal to 1. Therefore what do you think I have proved? Therefore conclusion, this is the major conclusion, is we have proved phi 1 composite gamma of t is 0 for all t in 0, 1. Therefore in particular gamma of 1 will be of the form 0 comma something. Okay, but according to us gamma of 1 must be equal to 1 comma 1. Okay, this is a contradiction. So what does this contradiction show? This contradiction shows that there cannot be a path joining 1 0 to 1 1. A small correction to what I said, gamma of delta 1, its x coordinate is 0, but remember gamma of delta 1 should lie within the open ball B P R, right? Therefore it will follow the point has to be 0 comma 1, because in that set there is only the one point which has a coordinate 0 coordinate, therefore x coordinate is 0. That is the reason why we chose R such that BPR does not intersect the x-axis, right? Therefore there is only one point whose x coordinate is 0, and therefore that point must be 0 comma 1. I hope you understand. Just let me quickly share the screen and explain if needed. Okay, so what we saw was for t in 0 delta 1, phi 1 composite gamma of t is 0, right? But remember phi 1 composite gamma of t, okay, lies in VP of R, intersection with x. Yeah, but this delta 1 may go outside, so it has to lie in, this is for 0 less than or equal to t less than delta 1. Therefore at delta 1, okay, gamma t has to lie in the closure, therefore it may be B close ball BP of R intersection x, right? But therefore gamma of delta 1 will lie here, but gamma of delta 1, if I write it as x of delta, okay, this coordinate, this must be 0 and this must be something, but in the closed open ball BP of R intersection x, what I am looking for, let me also choose R such that the closed interval BP of R, okay, the intersection x-axis is 0, is empty. Okay, therefore in this the only point which is part of x, also whose x coordinate is 0, is 0 comma 1. Therefore gamma of delta 1 is 0 comma 1. Now repeat the proof as earlier, replacing 0 by delta 1. That's it. Okay, I'm sorry for the goof off. Okay, I had that in mind, but when I'm lecturing sometime, okay, I'm more interested in explaining to you, so I forget to think. Okay, even though I also always want to think when I teach, but sometimes it becomes difficult even for me. Okay, okay, please go through the proof. Okay, understand LEV thing and try to mimic the proof for the first part at delta 1. Okay, in earlier we said gamma of 0 is 0 comma 1, therefore pi 1 of gamma of 0 is 0, etc. Okay, now we use the same thing, replace 0 by delta 1, mimic the proof. Okay, therefore I can extend 0 to delta 1 to something delta 2 which is greater than delta 1 if delta 1 is not equal to 1. Yeah, that's a crucial thing. Okay, please go through the proof, and toward the end you may find it difficult, but go through it second time, think, but spend more time in the beginning of the proof. If you had understood that, then you will see how to repeat the proof, okay, at delta 1 also. Okay, I hope you enjoyed this. Okay, this ends the path connected series. We will meet again, possibly about compactness. I'm not very sure what I will do, but let us do that. Thank you very much.